Q&A session. So to start, it's my pleasure to have Patrycja here. She's a research assistant, a PhD student in our group, and she'll be talking about machine learning workflows using Pegasus. Patrycja, the floor is yours.
Welcome everyone. My name is Patrycja, and during this presentation today, I will focus on machine learning workflows and talk about our group's exploration efforts and growing experience with building machine learning workflows in Pegasus. More precisely, I will describe the general picture of machine learning workflows, overview each of the steps involved in developing ML experiments, while at the same time highlighting some of the currently available Pegasus features that can support these steps. And lastly, I will introduce a team of students in our lab who work on porting scientific machine learning workflows to Pegasus and talk a little bit about their work. So it's of course hard to overemphasize the prevalence and importance of machine learning in the world of current scientific research. Machine learning has profoundly influenced a wide range of scientific applications, including drug development, astronomy, agriculture research, and most recently in biology, the development of DeepMind deep fold architecture is set to lead to many more discoveries and breakthroughs in medicine and beyond. So let's talk about how those workflows that lead to all these great discoveries look like. And one way to look at machine learning workflows in very high level is to see them as comprising of 3 sequential stages. In the first stage, we do all the data-related steps. Then there's a learning component, and lastly, we have validation and analysis. And each of these stages has several sub-steps to them and techniques associated with them. As you can see, they also have, we can iterate through them multiple times, and there are feedback loops between them. In more detail, we can see a machine learning workflows as comprising of 7 distinct steps. First is data acquisition, then data preprocessing, some data transformation. We want to do some hyperparameter optimization, then train our model with the best hyperparameters, do inference, and finally evaluate the results of our model. And I'm going to talk about these steps based on an example of land cover classification. This comes from a recent publication on using high-resolution remote sensing images to do a land classification with transfer learning. So as you can imagine, having such a data set with ground truths that have very detailed segmentation of land is very expensive. So there is only limited amount of labeled data. And that's why the researchers decide to use transfer learning, which are the models that are already trained on the ImageNet dataset and use the features from them. And the result of the paper is this architecture. And we can say that this view in the paper of the final results and the model can obscure from us of how, what is the true nature of developing machine learning model, which is very complex, iterative, and we're gonna now talk about all the steps that it involves and how Pegasus can help. So first, of course, is data acquisitions. For the scientists to be able to perform the experiment, they had to download a huge amount of high-resolution images for their training set, as well as images for the testing, which were coming from different sensors. And here we can see that Pegasus could help us with the integrity check. Next, the data has to be split into a train, validation, and test sets to ensure integrity of our model. And some of the preprocessing steps that follow, they might have to be done separately on different sets of data to not lead to data leakage of information between sets and keep the integrity of our work. In the data preprocessing, here the researchers had to requantize the images, resize them, and with the help of Pegasus, this could have been done in parallel, taking the most of available resources. Then we have hyperparameter optimization, where the researchers try to find the best set of hyperparameters to make their model perform with the highest possible accuracy. And in exploring different hyperparameters, here for this model, it was, for example, a segmentation scale, and we can see how the different level of segmentation leads to different overall accuracy of the model. And what is really important when doing hyperparameter optimization, despite of perhaps being able to do it in parallel and exploring different settings at the same time, we also want to make sure that we are doing a good checkpointing and have a good data tracking, so we know which data was used to train which model. Then finally, once we have our model, our best hyperparameters, we can retrain the model. So the set of validation images that we use to find the best hyperparameters can be now part of our training set, and the model has to be retrained again. And here we can use again the checkpointing feature of Pegasus to make sure that if we are training a model for a very long time and the node will go down, we have a checkpoint to restart the training. And at the end, we are doing model evaluation. Here we can see how the authors use the image and the grand truth data to compare their results to results of other researchers. And this workflow that have seemed so as just a small architecture, really, if we follow the paper and describe all the pieces that are happening at different time, we can get this much more complicated, but still simplified here view of what that workflow look like, that it's actually two different workflows because there has to be some pre-training being done, and later we optimize the hyperparameters actually for different sources of the image data. So the training set comes from one type of a sensor, and if we want to train models with the highest accuracy for other sources of images, we have to do it specifically per image source. So this is a more true picture of that workflow and how it looks like. And there are definitely a number of features already available in Pegasus that can support executing of such a workflow. And we are trying to learn more about the characteristics of machine learning workflow and how we can support those workflows in the future by having a group of students working in our lab who port machine learning workflows from a published work. And here we see all the students and projects that they work on. Our youngest student is Kelsey Liam, who is a high school student. She works on a workflow for mask detection and classification. And when we first conceptualize the workflow, we usually make a chart like that shows different machine learning steps of the workflow. And then we find the best way to map it to Pegasus and utilize different features of Pegasus to execute this workflow. So more closer to Pegasus view of this workflow looks like that. The data is split, and then this, for example, a data augmentation job here could be done in parallel on many nodes. We use checkpointing and so on. And this is a very impressive work by our high school intern. Then we also have master students working in the group. Surjana is working on porting a galaxy classification workflow. And here we can see when she's designing the workflows based on the paper and publicly available code. This is the graph that is guiding her work and her implementation of the workflow in Pegasus. Yet another student is working on the long segmentation workflow. So basically in the group, we are trying to work on different types of machine learning, different tasks, whether is it classification or segmentation, use different framework and learn as much as we can about those workflows so that we can support them better in Pegasus. Here's just how it looks on the Pegasus deck. Thank you very much.